Welcome everybody. Today I'm going to be talking to you about the WaterSENSE project, and in particular the water use monitoring and auditing service, known as WMAS. So WaterSENSE is a EU-funded Horizon 2020 Research and Innovation Program grant made up of a consortium of small and medium enterprise organizations from the Netherlands, Germany, Portugal and Australia. So here in Australia, it's the University of Sydney and Water Technology ourselves. From the Netherlands, the project is led by eLeaf, which is a company that specializes in remote sensing products and services. Hydrologic Research, which are the developers of the HydroNet platform, the platform cloud-based subscription service platform through which most of the applications, including the WMAS application, will be delivered. Hydro and Meteo in Germany are specialists in weather and radar rainfall and nowcasting products, and Hidromod in Portugal are water modeling experts, with HCP International being Mark Nuert, a expert in project coordination for us. Our participation in GEO is that we will be contributing partners to EuroGEO, and we are part of the GEO Global Water Sustainability Initiative, GEO-GLOS, and we will be planning to make during 2022 and 2023 further contributions to AfriGEO, MREGEO, and AOGEO. The general approach for the WaterSENSE project is this co-creation, double-loop learning feedback process of testing, feedback, and adjustment. So we have work package 1, which is the initial understanding of the market and the user needs and the value chain. And then the number of technical work packages, which will be developing the services. And those services will then be demonstrated with demonstration partners, prototypes, who will be working with us to provide feedback and learnings that can then be used to adjust those applications until they are finally ready for market. Our current demonstration partner for the WMAS application is the New South Wales Government Department of Planning, Industry and Environment. We're very happy to have them on board. There are 4 prioritized WaterSENSE services that we will be developing in this project. I already mentioned the water use monitoring and auditing service, and highlighted in red is what I'll be talking to today, which is the irrigated water use determination and comparison with authorized and immediate water use. We also have water counting, regional agronomy decision support, environmental flow management and decision support services with a number of modules that we plan on demonstrating during the product. But today it's just the WMAS and irrigated water use determination that we'll be talking about. So what is WMAS? WMAS is a satellite-based water use compliance check. It's based on the ET-look and HSP, or hydrologically similar pixel algorithm, and calculates the actual crop evapotranspiration due to irrigation per field across an entire catchment, and then can compare that estimated water use for irrigation with the actual allowed or allocated or authorized licensed water use. And it's a planning tool across the catchment that allows you to identify where inefficient water use may be happening, or easy identification of big water users or potential unlawful water users. And we'll be demonstrating this in the Namoi catchment, which is one of the large basins of the Murray-Darling Basin, as you can see here. So the Namoi is highlighted in red there, and that's our demonstration area with the DPIE. If we zoom into the Namoi, you'll see we also have an area of interest, and that area of interest is covered by one of the higher resolution Sentinel satellite tiles, and in that area we'll be demonstrating the same products but at much higher resolution, 10-meter spatial resolution, for example, whereas the larger catchment or entire basin or state or country is at 300-meter resolution standard product. So this collaboration with the DPI is presented in this slide. So on the left is WaterSENSE and the various algorithms that I'll go through, the ET-look algorithm, the hydrologically similar pixels, and then the aggregation of that raster information to farm units and fields. And clusters, which is on the right hand side, and clustering, the lot clustering algorithm is what the DPIE have been working on, and it's quite an intensive process to be able to come up with polygons at which we can compare the allocated licensed water use to the remotely sensed data. So I'll talk to the clustering first. The DPIE have been done. So here you see a typical river with a lot of abstraction points on it that each have abstraction IDs attached to them. And then you have a number of lots or properties, and within those lots works like a pump, for example, or a dam. And you can see that there are a lot of work authorities, different types of access licenses, shares, trades, carryover water, annual water demands all feed into those licenses. But one license or one work authority is not linked to one particular work or particular lot. It can be linked to a number of works and a number of different lots. So therefore you can't compare what you're picking up on a particular field with a particular lot. You have to cluster them into a group of lots that can all be linked to a set of licenses. And that's what the DPIE have now done, and have set up an API that we can access as a WaterSense project to get these clusters and understand which fields and which lots are associated with those clusters and what are the licenses, and therefore do those comparisons. So that's been probably 18 months of work and revision just to get this clustering algorithm to where it is right now that can be used in an application. Now I'll talk to the actual WaterSense application and the various models and tools that we are using for this application. So the first one is the ET-look algorithm. This is generally based on the Penman-Monteith equations. It's raster-based satellite imagery and weather data is brought in, and it calculates physical energy balance modeling. It's originally based on the CBAL algorithm, but it's basically an evolution of that CBAL algorithm to the ET-look algorithm now, and this is attaching this CBAL algorithm as it is amended to an automated processing facility, and enabling it to also be calibrated per region or area and not just specifically to an image. So this ET-look algorithm basically calculates the evapotranspiration of a pixel. We then put that into the hydrologically similar pixel algorithm, which takes an irrigated pixel that we have already know is irrigated due to the land cover mask that we were provided by the DPIE, and for each irrigated pixel, the hydrologically similar pixel method takes a radial approach looking for similar non-irrigated pixels that have a similar natural vegetation, and uses a lot of static input data like gradient, aspect, wetness index, soil texture, and other factors to determine the 50 most similar natural pixels. The average or median evapotranspiration of those natural vegetated pixels is then compared to the evapotranspiration of the irrigated pixel, and the difference is with some adjustments and calibration considered to be applied irrigated water use. And that's pretty much how the irrigated water use estimated per pixel is calculated, and that is what the HSP method or algorithm does. Once that's done per pixel, and for each field unit that we have in the system, those pixels that are irrigated and the incremental ET is then aggregated to a field, and you are provided with an estimated irrigated water use in millimeters or megaliters per farm unit or per field. And then the final step is then actually able to aggregate each of those fields further up into clusters, and then at cluster level of fields and lots you can then compare to the allocations. And all of this is then provided through the HydroNet dashboard as an application, as a subscription service application. The rest of this presentation is basically about how that application looks. So in our discussions with the DPIE, we came up with three major dashboards. One is to just present the water use that the remote sensing is estimating. So on the left is the megaliters, and on the right is the megaliters per hectare, or the application rate. You can use a search functionality to search for a cluster or for a license, for example, and it will then zoom you into that cluster or field or lot or license. So if I typed in here cluster 951, it will then zoom me into the 951 or the field, and then highlight it as you see here on the left hand side. You can then click on any of these clusters or fields, and you can get a chart of the actual water use that's there. The second water dashboard is the water use difference dashboard, which is comparing what the satellite or the metered water use is estimating to the actual allocation that's been given for each cluster. So on the left, what you see in red is for the year the cluster has possibly exceeded the allocation, And on the right is an example of charts that you can get when you click on those polygons to compare the actual regulated or groundwater or unregulated water use to the remote sensing and to the allocation as well. And the final one is the availability balance, which is comparing specifically to how much of your allocation is left. So on the right is an example of where I've clicked on a field and you can see the allocation. The user actually had a small allocation, they purchased more water and it jumped up in the second month, and then it's been slowly been used not very much, and they still have a large allocation balance left for that particular field or cluster. Actually not field. So the results. So we have done some quick calibrations or validations of this. There's still more validation that needs to be done, but it's looking pretty good at an annual level. What we have observed, however, is that there are some differences on a month-to-month basis between this observed satellite water and the metered water use, and there are a number of reasons that can be attributed to this. The main one is the fact that the meters are actually not at the field, they are at the resource, the borehole or the river, and in many cases irrigators are pumping from that resource into large farm dams and not onto the fields at the same time. So when you're getting records on your meter, it's not necessarily the same time you're applying that to the field. And you can see that example in these two images where on the left hand side there's an empty dam and on the right hand side there's a full dam. And during that time the meter would have been showing a lot of water use, but there was actually no change in the fields because it wasn't applied to the field. So it's very important to get an understanding of how the dam area or dam volume change is affecting the balance for the cluster or for the farm. There's also water losses and type of irrigation and accuracy of the land use classification that's used in the first place, not necessarily covering all the land that is irrigated. So one of the things that we will be doing in the remainder of WaterSense is actually researching a dam volume change algorithm that on the time step bucket will calculate not just the area change of the dam, but also an estimated volume change, and that can then be applied to the balance to better compare on a monthly basis the metered water use at the resource to what we are picking up on the field. So that was a very quick brief overview of the water use monitoring and auditing service application of WaterSense and a little introduction to the WaterSense consortium. If you would like to follow us, then please go to LinkedIn Project WaterSense or on Twitter at MakeWaterSense, or you can contact myself in Australia or Stephen Wonink in the Netherlands for international global aspects. Thank you very much for your time.